Okay, so those who have joined the class of finite element analysis may give their attendance in the chat box. I repeat, those who have joined the class of finite element analysis may give their attendance in the chat box. Just give me a minute so that I can present my screen. Can anyone please respond whether my slides are visible or not?
Yes, sir, they are
Okay,
visible.
and am I audible?
Yes, sir, of course.
Okay, thank you. Okay, so before starting today's class, let me give you a brief recap of what we have did in the last class. If you remember, in the last class, we have taken up a problem in which the cross-sectional area was varying continuously. That is, this is nothing but basically a taper problem. This problem we have taken and we have divided this entire problem into some finite number of elements, and then by that stiffness method we have found out what will be the nodal displacement and nodal stresses present in each of the finite element due to this 12 kilonewton load. So in today's class, what we will discuss is the effect of temperature in static structural analysis. This is nothing but the thermal stress, effect of thermal stress in static structural analysis. Already you have did this part in strength of material, fine, but here we will not be solving by strength of material approach. We will be using finite element method approach to solve the problems in which or to solve some static structural problems due to some effect in temperature. For example, if you consider a bar element of uniform section, that means this is your bar element. This is your bar element of uniform cross sectional. That means cross section is same throughout the element. Length L. Assume that the length of this bar element is L. It is having a coefficient of thermal expansion alpha. This bar is having a coefficient of thermal expansion alpha. It is subjected to a change in temperature delta T. That means due to some phenomena, what is happening? Some change in temperature of the bar of this bar is happening. Fine. So in addition to the applied load, that means earlier what we were doing, that this is a bar of length L, and if this bar is subjected to some load, then what are the different nodal displacements that we will get if we divide this bar into some finite number of element. But in this case, with the presence of applied load, there is some temperature differences also present in this bar. Let alpha is what? Alpha is the coefficient of thermal expansion, which is nothing but the property of the material. That means I know that if for a particular material, if coefficient of thermal expansion alpha is very high, that means that particular bar will expand more as compared to the other bar whose coefficient of thermal expansion alpha is low. By that sense, we can say that yes, the first bar will be subjected to tensile thermal stresses, or the second bar will be subjected to compressive thermal stresses, and so on. So if we assume, let epsilon t, small t, is what? It is nothing but the total strain experienced by the bar due to temperature and the applied load. That means due to this applied load and due to change in temperature of the bar, this bar will either elongate or will contract. That elongation or contraction is denoted by thermal, by the symbol called epsilon t. What is epsilon t? Epsilon t is the total strain generated in this bar due to this static structural load P and due to change in temperature delta T. Fine. And let epsilon capital T is what? It is nothing but the strain developed in the bar due to temperature delta T. That means when this bar is either when this bar is heated or cooled by some amount of temperature, say that temperature is delta T, then the thermal strain present in this bar will be nothing but epsilon capital T. So this epsilon capital T is the strain. Which strain? This is thermal strain due to change in temperature delta T. And what is this epsilon T? Epsilon T is the strain generated generated in this body due to this static structural load as well as due to change in temperature delta T. Then the net elastic strain, that is epsilon E, is given by epsilon T small t minus the temperature strain epsilon capital T. Is this expression clear to all of you? This you already know from the concept of strength of material. Any doubt so far?
No, sir.
Okay. Other people please respond whether it is clear or not. Hello. Other people please respond whether it is clear or not.
Yes, sir, clear.
Okay, so I also know is we have derived this relation in strength of material that this thermal strain epsilon T is given by relation epsilon T is equal to alpha times of delta T, where alpha is the coefficient of thermal expansion and delta T is the change in temperature of the bar. Okay. Then by Hooke's law, since we are talking about static structural analysis, so if I apply Hooke's law, what Hooke's law says that within the elastic limit, stress is directly proportional to strain. Epsilon E is the total strain present in this bar due to change in temperature of the bar delta T. Then according to Hooke's law, the stress is directly proportional to total strain epsilon E, or stress is equal to one constant of proportionality, that is capital E, into total strain epsilon E, and this capital E is your modulus of elasticity, and this epsilon E we will substitute by epsilon T, that is the strain developed in the bar due to change in temperature as well as due to applied load, minus epsilon capital T, where epsilon capital T is the strain generated in the bar due to change in temperature. Fine. So I know that in FEM we have to represent each and every equation in matrix form. So if I represent this particular equation in matrix form, how I can write? Sigma is equal to E into, now this is what? This is nothing but strain. In last few classes we have seen that strain is what? Strain is equal to strain displacement matrix B into strain displacement matrix B into nodal displacement vector Q. Fine. So I can write this expression, that is epsilon T minus epsilon capital T, as strain displacement matrix B, that is this epsilon T. This epsilon T is what? This is nothing but the total strain present in the bar due to the applied load as well as change in temperature, that is B into Q. See, this is strain displacement matrix B into nodal displacement vector Q minus, and what is this epsilon capital T? Epsilon capital T is nothing but thermal strain, which is nothing but given by alpha delta T. So finally, the expression for stress in matrix form for any element becomes sigma is equal to E bracket strain displacement matrix B into nodal displacement vector Q minus alpha delta T. Is this equation clear to all of you? With this equation, we can find out the stress generated in each and every element of a bar which is subjected to some thermal stress or thermal strain. Is it clear? Any doubt so far?
No, sir.
Okay. Similarly, we can also calculate the nodal force vector. That means if I am having a bar, if I divide this entire geometry into say 3 finite elements, then each node will be experiencing some forces. Fine. That force value is given by this expression. That force value is given by, because we know that the governing differential equation, governing algebraic equation is what? It is nothing but global stiffness matrix into global displacement vector matrix is equal to global force vector matrix, and this global force vector matrix is nothing but this matrix. That is F bar is equal to F. What is this F? This F is the force or the load present in the bar. That is static structural load present in the bar. Plus, this is load present in the bar when that bar is undergoing expansion or compression due to change in the temperature delta T, and that is given by A into E alpha delta T, again 2 cross 1 matrix minus 1 1. So the final equation or the final expression for the nodal load vector or force vector becomes F bar is equal to F matrix F plus A into E alpha delta T 2 cross 1 matrix minus 1 1. So if I say that this is my bar, and say this is the first element of the bar, then I know that this is my node number 1 and this is my node number 2. Then for this element, if I want to write this nodal load vector equation, how I will write? That is F element, that is for first element, is equal to this value. If it is present, I will take into account. If it is not present, I won't take, plus this particular value. Now see, this element number 1 comprises of two nodes, node 1 and node 2. Each node will be subjected to some forces. Then I can write it as F1 F2. It is 2 cross 1 matrix. F1 F2, that is this value. F1 F2 is equal to F static structural load. If it is present in any node, I will take. If it is not present, I won't take. Plus this particular expression, that is A into E alpha delta T 2 cross 1 matrix minus 1 1. So by this expression, we can find out the nodal force vector present in any element when that element is subjected to some thermal kind of stress. Is it clear? Any doubt so far?
No, sir.
Okay. Other people, please respond whether it is clear or not. Hello.
Yes, sir, clear.
Okay, so now what we will do, we will take the help of these expressions and let us solve one problem by finite element method, and then let us find out what will be the element stresses and elemental load vector if that particular element or the entire geometry is either heated or cooled by some amount. Say that amount is delta T. So let us solve a problem. So let us read this problem. The problem tells you that a composite bar ABC made of aluminium and brass is shown in the figure. It is subjected to an increase in temperature of 100 degrees centigrade. That means delta T value is given to me. This increase in temperature is nothing but delta T. So delta T given is 100 degrees centigrade. AB is made up of brass. This AB is made up of brass and BC is made up of aluminium. Okay. AB is made up of brass with area 1200 millimeter square. That means area of AB is 1200 millimeter square and the length of AB is 400 meter. That means this particular length is how much? It is 400 meter. Modulus of elasticity is 105 gigapascal. That means for brass, modulus of elasticity is 105 gigapascal. That means value of E for AB is 105 gigapascal and coefficient of linear expansion is 18 into 10 to the power minus 6 per degree centigrade. That means for bar AB alpha is given to you. That is how much? 18 into 10 to the power minus 6 per degree centigrade. BC is made up of aluminium with area 1500 millimeter square. That means area of BC is 1500 millimeter square and its length is 500 meter. That means this length is given to me. This length is how much? It is 500 millimeter. Modulus of elasticity is 70 gigapascal. That means for this BC bar, value of E is how much? 70 gigapascal. And coefficient of linear expansion is 23 into 10 to the power minus 6 per degree centigrade. That means for this bar BC, which is made of aluminium, alpha given is 23 into 10 to the power minus 6 degree centigrade. Compute the stresses developed in the two material by direct stiffness method. That means whatever method we are following from past few classes, we have to follow that same method to get the value of stress developed in the two material. That means what is the value of stress in bar AB, what is the value of stress in bar BC by direct stiffness method. Only difference in this problem is in this problem the entire geometry is subjected to an increase in temperature of 100 degrees centigrade. For both the material alpha is given to you. So what will happen? In this particular problem, whatever we have did in the last class, addition to that, we have to calculate the thermal stress, thermal strain. We have to incorporate these thermal stress and thermal strain in my matrix, and then we will get the value of the stress developed in the bar AB and bar BC. So is the concept clear about this question? Any doubt so far? Hello.
Yes, sir. Yes, sir. It's clear.
Okay. Krishanu, Orko, if you all can respond whether it is
Yes,
clear.
sir.
Okay. So again you see the in this problem nowhere it has been told to you that in how many elements you have to divide the problem. If nothing has been told, that means I have the freedom. So what I will do is let us divide the entire problem into four finite elements. Since AB is one material, BC is another material. So what we can do? We can divide AB into two elements, element number 1, element number 2, and we can divide BC again into two elements. Then this will be element number 3 and this will be element number 4. Is it clear? The division of elements? Any doubt?
No, sir. No, sir. No doubt.
Then
No,
if you
sir.
divided the AB into two equal finite element, definitely the length of element 1 is nothing but half of AB. Length of element 2, again it will be nothing but half of AB. Length of element number 3 will be nothing but half of BC, and length of element number 4 is nothing but half of BC. Is it clear? Any doubt? Hello.
No, sir. No, sir. No doubt.
So that means I can say that this is my node number 1, this is my node number 2, this is my node number 3. Fine. This is my node number 4, and this fixed end is nothing but my node number 5. So in altogether, the entire problem is divided into 4 finite elements containing total of 5 nodes. So can you tell me that what will be the size of the final assembled or global stiffness matrix for this problem? Can anyone tell me what is the size of the final global assembled stiffness matrix for this problem? Krishanu?
The
Hello?
6 by 6, I think.
How come 6 by 6? Total 5 nodes are
Oh, sorry,
present.
sorry, sorry.
Four
5 by 5.
elements are there. So the size of the final
5
global
by 5.
stiffness matrix will be a 5 cross 5 matrix. 5 rows, 5 column. Each row and each column represent particular node. And one and two boundary conditions are also given in this problem. Can anyone identify those two boundary conditions present in the problem? Two boundary conditions are given in the problem. If you see the diagram, from the diagram you can clearly find out two boundary conditions. Can anyone tell me what are those two boundary conditions?
Sir, the means extraction of that material should be up to 0.6 mm.
That means I
Yes,
can
sir.
say that if this is my element number 1, definitely this will be my node 1, this will be my node 2. That means if you see left hand side, there is a gap of 0.6 mm from the left fixed support till the nodal point 1. So for equilibrium condition, the bar AB will displace by an amount 0.6 mm in negative x direction, or in other word, if I say node 1, displacement of node 1, if I assume that displacement of node is nothing but u, then displacement of node 1 should be equal to minus times of 0.6 mm. Then only the equilibrium condition will be maintained. Yes or no? Yes or no?
Yes, sir. Yes, sir. Definitely.
And why I have taken minus? Because if you see, this AB will move towards the negative x direction.
Yes,
So if
very.
I assume the displacement of each node along a positive x direction, then definitely the value of u1 will be minus 0.6 mm. This is one boundary condition. One more boundary condition is given to you. One more boundary condition is given to you. Can you tell me what is that boundary condition? One more boundary condition is given to you.
Sir, that it's a cantilever beam.
Can anyone tell me? One more boundary condition is given in the problem. And that boundary condition is, if I see node 5 is fixed, if node 5 is fixed, then that particular node will not move. If that particular node will not move, then displacement of node 5 is how much? It is 0 mm. Yes or no?
Yes, sir. Sir, why bol?
Okay. So is it clear these two boundary conditions, that u1 will be minus 0.6 mm and u5 will be 0? Is anyone is having any kind of doubt in these boundary conditions?
No, sir.
Okay, other people please respond. Hello, hello. Other people please respond whether any doubt is there or not. Okay, if you are not responding, I will assume that you are not having any kind of doubt. Fine. So the very first step is what? The very first step is we have to divide the entire problem into some finite number of element. So we have divided the entire problem into four finite element, four finite one-dimensional element. Why one-dimensional? Because by looking at the problem, it is very much clear that each particular node of element will move along only in one direction. So see, we have divided the entire problem into four finite number of element. Each element is surrounded by two nodes. Fine. And let u1, u2, u3, u4 and u5 are the corresponding nodal displacement along positive x-axis. If at last my answer of u1, u2, u3, u4 is coming out to be negative, that means I have taken the wrong direction of displacement. Displacement will be in opposite direction. Is it clear so far? Whatever I have told, any doubt so far?
No, sir.
Okay. Next step is what? Next step is construction of element attribute table. Next step is construction of element attribute table. Fine. So first column is what? Elements. So in altogether, how many elements we are having? We are having total four elements. So element number 1, 2, 3, 4. Next column of element attribute table represents node connectivity of a particular element. Element 1 is connected between node 1 and 2. Element 2 is connected between node 2 and 3. Element 3 connected between node 3 and 4. And element 4 connected between node 4 and 5. Next table is the length of each element. Now since it is given in the problem that AB is having a length of 400 meter. AB is having a length of 400 meter. We are dividing AB into two equal parts. Then each equal finite element will have a length of 200 mm. That means zero point 0.2 meter. So element 1 and element 2 both are of 0.2 meter. Similarly, if you see the problem, the overall length of the element BC is how much? It is, I think, it is how much? 500 mm, and we are dividing the bar BC into two finite elements. So each individual element will have a length of 500 by 2, that is 250 mm or 0.25 meter. So for element number 3, the length is 0.25 meter, and for element number 4, the length of the element is 0.25 meter. Next is area of each element. If you see in the problem, directly the area is given to you that AB is made up of brass whose area is 1200 mm square. Since from AB I am getting the first and the second element, so area will be same for first and second element. So in meter square, that value is coming out to be 1.20 into 10 to the power minus 3 meter square. Similarly, the cross-sectional area of the bar BC is how much? It is 1500 mm square, and when we divided the bar BC into two finite elements, we got element number 3 and element number 4. So element number 3 and element number 4 will also be having an area of 1500 millimeter square. That is nothing but 1.50 into 10 to the power minus 3. This is the area. Next is the modulus of elasticity of each element. Again, if you see the problem, it is given that for brass element, that means for AB is nothing but made up of brass. Value of E is 105 gigapascal. That means element number 1 and element number 2 value is 105 gigapascal, and since BC is made up of aluminium whose E is 70 gigapascal. So element number 3 and 4 are coming out from the bar BC. So element 3 and 4, the value of E is how much? 70 into 10 to the power 9 Newton per meter square. Next step is what? Finding out the stiffness value. Since we have to make the stiffness matrix, so we need to find the stiffness value. We know that stiffness is given by the expression E into A by L. So for first element, this stiffness equation becomes E into A1 by L1. A1 is how much? A1 is 1.20 into 10 to the power minus 3 divided by L1, length of that element. That is how much? 0.2 meter. If you solve it, you will get this particular value. Similarly, second element is also coming out from the bar AB. So its area will be same. That is 63 into 10 to the power 7 Newton per meter. And similarly for element 3 and element 4, since element for element number 3 E is how much? 70 gigapascal, because the material is made up of aluminium. A is what? A3, this is my A3, into 1.50 into 10 to the power minus 3 divided by L3. L3 means length of element 3. Length of element 3 is 0.25 mm. Once you solve that expression, you will get the value of stiffness of that particular element as 42 into 10 to the power 7. Similarly, the stiffness value for the fourth element will be exactly same and identical as that of element number 3, and the value is 42 into 10 to the power 7. So is it clear so far, the element attribute table? Any doubt?
No, sir. No, sir.
Okay. Once we have tabulated this element attribute table, next step is what? Next step is for each and every element individually, we will find out the stiffness matrix. We know that stiffness matrix is given by expression, that is E into A by L. It is a 2 cross 2 matrix, and element of the matrix is 1 minus 1 minus 1 1. The first row represent first node, second row represent second node of any particular element. So for element number 1, stiffness matrix K1 is how much? E into A1 by L1. 1 minus 1 minus 1 1. And since element number 1 is connected between node 1 and 2, so the first row becomes node 1, second row becomes node 2, first column becomes node 1, second column becomes node 2. See, I have did it with the red pen. 1 2 1 2. So already we have calculated for first element E into A1 by L1. That is how much? 63 into 10 to the power 7. So what we can do is we can multiply 63 with each element of the matrix. Then the final matrix is nothing but equation number A. That is 10 to the power 7, 63 minus 63 minus 63, 63. Is it clear so far till first equation, that is equation number A?
Yes, sir.
Okay. Similarly, element number 2, since element number 2 is again coming out from the geometry AB, so value of stiffness matrix again will be same, because value of K is same. Only what will change? The pattern, the way of writing the node number will change, because element number 2 comprises of node 2 and node 3. So the first row will become 2, second row will become 3, first column will become 2, second column will become 3. That is equation number B. Again, then the final expression becomes 10 to the power 7, 2 cross 2 matrix, 63 minus 63 minus 63, 63. Is it clear till equation number B? Any doubt?
No, sir.
Okay, other people please respond whether it is clear or not. Hello. Others please respond whether it is clear or not. Okay, if no one is responding, I will assume that this thing is clear. Similarly, I can write the stiffness matrix for the third element. And for the third element it will be how much? E into A by L. E is nothing but 70 into 10 to the power 9 into A. A is your A3, 1.50 into 10 to the power minus 3 divided by L3. L3 means length of the third element, which is 0.25. So if you solve this particular expression, fine, you will get some value of K. Again, I can write the stiffness matrix for the third element. Only what will change? The way of writing the row and column number will change. If I see for third element, the node connectivity is from 3 to 4. So the first row will become 3, second row will become 4. Similarly, first column will become 3 and second column will become 4. That is nothing but equation number C. That is K3 is equal to 10 to the power 7, 2 cross 2 matrix, 42, minus 42, minus 42, 42. Is it clear so far till equation number C? Hello?
Yes, sir. Yes, sir. Yes, sir.
Fine. Similarly, for element number 4, again the stiffness matrix will be same because value of K is same, value of E is same, area is same. Only what will change? The way of writing the row and column will change. Because I can see that for element number 4, nodal connectivity is from node 4 to node 5. So the first row will become 4, second row will become 5. Similarly, first column will become 4 and second column will become 5. That is equation number D. Is it clear? Any doubt so far?
No, sir.
Please respond whether it is clear or not.
Clear, sir. Clear.
Okay, fine. So next step is what? Next step is we have to now write the assembled global algebraic equation or governing algebraic equation for the problem in matrix form. But before writing that equation, first I have to get the global stiffness matrix or the assembled stiffness matrix for the entire problem, and that will be given by, if we add equation A, B, C and D, then we can get the assembled or global stiffness matrix. And the size of the matrix, again it will depend upon the total number of node present in the element. Since total number of element is equal to 4, so total number of node will be 4 plus 1, that is 5. So then I can say that yes, this global stiffness matrix is nothing but a 5 cross 5 matrix. The first, second, third, fourth and fifth row, as well as first, second, third, fourth and fifth column, represent corresponding nodal values, corresponding node points. That means first row represent node 1, second row represent node 2. In similar way, the third column represent node 3 and fourth column represent node 4. So how to get this global stiffness matrix? From equation A, B, C and D, you need to get this particular element. That means K11. This is what? This is K11, K12, K13, K14, K15, K21, K22, K23 and so on. Fine, you have to find this 1 from A, B, C and D. If it is there, write that value. If it is not present, just make it 0. Similarly, you need to find, say if I talk about this 2, this particular element, that means K22. That means K22 means now I have to find this second row and second column, this particular value from equation A, B, C and D. Let us find out. So from equation A, 2 is how much? It is 63. From equation B, 2 is how much? 63. From equation C, there is no 2, and in equation 4, no 2. So the final value of this 2 is what? I told I have to add A, B, C and D stiffness matrix equation. So when I am adding 63 with plus 63, that value is coming out to be 126. Likewise, you can frame this 5 by 5 stiffness matrix. Is it clear? Any doubt so far?
No, sir.
Okay. Alok, Arko, Shaikar, if
Yes,
you
sir.
can.
It's clear. Clear, sir.
Hello.
Yes, sir. It's clear.
Okay, fine. Now I can write the governing algebraic equation for the problem, and that will be how what? That is your, yes, this is that equation. That is k into u is equal to f, where k is what? Assembled global stiffness matrix. U is what? U is assembled global nodal force vector. Since total 4 elements are present and 5 nodes are there, so this matrix, this U matrix will be a 5 cross 1 matrix. See, along the first row, displacement of node 1, along the second row, displacement of node 2, along the third row, displacement of node 3, and so on. So it is, this is my global stiffness matrix into my global nodal displacement values, that is u1 6 cross 5 cross 1 matrix, that is u1 u2 u3 u4 u5 equal to, now this is what, this is the force matrix, that is global load vector matrix. Now first, since the problem is a composite problem, first we have to find out that how much force is exerted by each element. So for that, we can use this particular equation. I have told you just now which equation, that is this particular equation we can use, that is f bar is equal to f plus a e alpha delta t 2 cross 1 matrix minus 1 1. This we will apply for each of the element to get the nodal force value. So let us find out. See, we know that f bar is equal to f plus matrix f plus a into e alpha delta t matrix minus 1 1. Again, what is this f bar? F bar is nothing but 2 cross 1 matrix, which is fi fj. And what is this fi fj? Fi represent force, acting force for any element at the ith node. That means if I am say if I consider this element, if this element is E and node is I and J, then this Fi represent nodal force present at the ith node. Fj represent nodal force present at the jth node, which is equal to, again, nodal force vector F plus A E alpha delta T 2 cross 1 matrix minus 1 1. Now in this problem, the entire this value of F is 0. Why 0? Because if you see the problem, nowhere in the problem any external load is applied, so that global force vector will always be equal to 0. That means this value is 0, this value is 0, then the final equation becomes fi fj equal to a e alpha delta t minus 1 1. Now if I talk about element number 1, this is my element number 1. Fine. Then I know that in element number 1 comprises of two load. One load is F1. At nodal point 1, the force present is F1, but it is for element number 1. Similarly, at nodal point 2, the displacement of node 2 is U2, and overall force at node 2 is F2. F2 represents force acting at nodal point 2, but for first element, and so on. Are you getting my point? Hello? Hello?
Yes, sir.
Fine. So if I consider element number 1, how I can write? For element number 1, nodal force vector present is F1 of 1, means force, that is force at node 1 for element 1. Force at node 2 for element 1 is equal to this particular expression. Now for element 1, A is given, E is given, alpha is given, delta T into 2 cross 1 matrix minus 1 1. Just solve this particular expression, you will get the nodal force present in the first element, and that is coming out to be F1 of 1 is minus 226800, and F2 of 1 coming out to be 226800. Equation number 1. Is it clear? Any doubt?
Yes, sir, it's clear. No doubts.
Similarly, for element number 2, again if I want to write the same expression for element number 2, how I can write? This is my element number 2. Oh, let me erase everything. Wait. This is my element number 2. Fine. Element number 2 comprises of two node 2 and node 3. Let us assume that nodal force present at node 2 is nothing but F2. But it is for which element? It is for second element. So F2 of 2. Similarly, nodal force present at node 3 for second element is what? That is F3. F3 means node present. F3 means node, that is nodal force at node 3. But for which element? For element number 2. Then I can use this expression. I can use this expression as for element number 2, it is a 2 cross 1 column matrix. That is F2 of 2. That is force acting at node 2 for second element. Similarly, F3 of 2, that is force acting at node 3 for second element, is equal to again this particular expression. For element number 2, again this value will be same because element 2 is generated from bar AB only. So A is same, E is same, alpha is same, delta T is same. Ultimately, you will get the same values. That is for element number 2, F2 of 2, that is called 2 cross 1 column matrix. F2 of 2, F3 of 2 is equal to minus 226800, 226800. Equation number 2. Is it clear? Any doubts so far?
No,
Hello?
sir.
Okay. Similarly, in the same manner, I can find out the nodal forces present in element number 3, which is given by equation number 3, and in element number 4, which is given by equation number 4. Once you have done these things, now you need to calculate the total nodal force present at each node. Total nodal force present at each node. If I talk about node number 1, total nodal force present is F1, which is minus 22,6800, minus 22,6800. Is there any F1 is there? No, it is not there. That means total nodal force at node 1 is minus 22,6800 Newton. Similarly, total nodal force present at node 2. So from equation number 1, I can see that total nodal force at node 2 is how much? That is 22,6800 Newton from equation number 1. From equation number 2, see, total nodal force F2 is nothing but minus 22,6800. In equation 3 and 4, it is not present. So finally, the total nodal force at node 2 is this 22,6800 plus minus 22,6800. That is, the value is 0. Are you getting my point? Hello.
Ah, sir.
Okay. Similarly, for element at node 3, total nodal force present is F3. F3. So I can see that F3 from equation number 1 there is no F3. From equation number 2 this is your F3, value is 226800. From equation number 3 this is my F3, value is minus 241500. And from equation number 4 there is no F3. So the total nodal force present at node 3 is how much? That is F3 of 2 minus F3 of 3, that is 226800 minus 241500, which is coming out to be minus 14700 Newton. Is it clear? Any doubt?
No, sir.
Okay. Other people please respond whether it is clear or not.
Yes, sir. Yes, sir. Clear.
So similarly, you can calculate the total nodal force present at node 4 and node 5. Then the nodal force vector, elemental nodal force vector is given by F is equal to 5 cross 1 matrix, that is F1, F2 and so on, F5, where F1 is how much? F1 is minus 226800 Newton. F2 is how much? 0 Newton. F3 is how much? Minus 14700 Newton and so on. Then we can write this governing algebraic equation. That means in governing algebraic equation, this K is what? That is global stiffness matrix. This is that matrix into U is what? Global elemental displacement. That is U1, U2, U3, U4, U5, since 5 nodes are present, which is equal to F. F is what? That is nodal force vector. Already we have calculated just now. That is minus 226800, 0, minus 14700, 0, 241500. Is it clear? Any doubt?
No, sir.
Okay. Krishanu and others please respond. Hello. Hello. Okay. So this is that expression. Now this governing algebraic equation which we have written, this governing algebraic equation which we have written, this is not correct. Why it is not correct? If you see, I know that yes. I know that at that is a displacement of node 1 is how much? That is 0.6 mm. Fine. And displacement of node 5 is how much? 0 mm. So I have to incorporate these values in this particular equation. That means this value of u1 is how much? 0.6 mm minus 0.6 mm in compressive direction, that is minus 0.6 into 10 to the power minus 3 mm, and this value of u5, it will be how much? It will be 0. So if this u1 is to be equal, if the value of u1 is equal to minus 0.6 into 10 to the power minus 3 meter, then if I make this value, fine, if I make this element value 1 and remaining row 0, similarly this column if I make 0, that means what I want to say is, if this is my 1, this is 0 0 0 0, this is 0 0 0 0. Now if you multiply, how you will multiply this row, this first row with this column, that means 1 into u1 is u1, 0 into u2 0, 0 into u3 0, plus 0 into u4 0 plus 0 into u5 0 equal to minus 0.6 into 10 to the power minus 3 mm. Are you getting my point? If u1 has to be, if u1 is equal to minus 0.6 into 10 to the power minus 3 mm, I have to make this particular element 1 and corresponding row value 0, similarly corresponding column value 0, then only I will get u1 is equal to minus 0.6 into 10 to the power minus 3 mm. Are you getting my point? Hello.
Yes, sir.
Fine. So for that, what I will do, just make that value 1. That means make in my first row, this first element, if I make 1, remaining element if I make 0. Similarly, in first column, except the first element, remaining element if I make 0, then I can write remaining matrix is same. From this 126 to this 42, remaining matrix is same, into u1, u2, u3, u4, u5 equal to, then this value, this minus 0.226800 becomes minus zero point 0.6 into 10 to the power minus 3 mm. It is correct. Is it correct? Remaining value is same. Remaining force value is same. Only this value I have changed. Now is the equation correct? First equation, if I write the first row in terms of matrix equation, now this equation will satisfy my boundary condition. Yes or no? Hello.
Yes, sir.
Fine. Okay, so this we got. Now, now see the second row. See, so if I talk about, if I see the diagram, fine. Second node, third node, and fourth node should be having some displacement values because they are not fixed. If they are not fixed, then the corresponding RHS side cannot be equal to 0. So if I see the second row, see this RHS is equal to 0. It cannot be equal to 0. Because if it is equal to 0, fine. So you will not get the value of u2. So somehow you have to make this 0 as a finite number. For that, what I do, is, now if I write the second, if I solve the given matrix equation considering the second row, what I can write, that means just multiply it, that is this particular row with this particular column. Fine, this is minus 63 into u1 plus 126 into u2 minus 63 into u3 plus 0 into u4 plus 0 into u5 equal to 0. That means this expression. Okay, now this expression is only valid when u1 is how much? U1 is minus 0.6 mm. So in place of u1, if I substitute minus 0.6 mm, that means minus 0.6 into 10 to the power minus 3. Fine. Then the resulting equation is nothing but this equation. The resulting equation is nothing but this equation. Fine. Just multiply 10 to the power 7 with this particular term and then bring this term to RHS. The final equation becomes 10 to the power 7 into 126 u2 minus 63 u3 equal to minus 37,800, which is nothing but now this value has been changed. Now it is C minus 37,800. Now if you will write the equation for the second row, with that equation you can get the value of u2. Earlier case you won't be able to get. Why? Because this RHS is equal to 0. You will not get the you will not get the value of u2. Are you getting my point?
Yes, sir. Yes, sir.
Fine. So I'm sorry I'm taking some long time, but I have to complete this problem. Okay. So please bear for that. Okay. So the resulting matrix becomes C 1 0 0 0 0 0 0 0 0. Resulting matrix is same into U1, U2, U3, U4, U5 equal to this value is your minus 0.6 into 10 to the power minus 3. Second RHS value is nothing but minus 337 800. Remaining value is same minus 14700. That is yes minus 14700 0 24 1500. ठीक है 24 1500. Fine. Now so we are done with this u1 part. Next is I can see that u5 is also equal to 0. So if I see the fifth row, and when I will write the matrix equation for this fifth row, then definitely this u5 has to be 0. When that means u5 is equal to 0. If u5 is equal to 0, this RHS value should be equal to 0, and u5 equal to 0 will only come if I make this element. This is what? This is fifth row and fifth column. This element as 1, and if I make it 0, remaining values are 0, and corresponding row if I make it 0. Now if you multiply, that is this row with this particular column, that is 0 into u1 plus 0 into u2 plus 0 into u3 plus 0 into u4 plus 1 into u5 equal to 0. Then this condition is satisfied. Yes or no? Yes or no?
Yes, sir.
Fine. So that means now since in order to use this boundary condition, that is u5 equal to 0, what I will do, and this particular element will be same as it is. I will keep it same as it is. So just do it. So you can see then the modified governing algebraic equation becomes this equation. See, this is 1 0 0 0 0 1 0 0 0 0 fifth row. See 0 0 0 0 1 and 0 0 0 0 1. Remaining matrix is same. Okay, and now see the difference. Here it was 24 1500, but it is not the correct equation because we will not get u5 equal to 0. Now this u5 you can substitute equal to 0. Okay, fine. Now if you use Gauss elimination method, since u5 is 0 and this RHS is 0, you can eliminate fifth row and fifth column. Similarly, from first row, you will only get u1 equal to minus 0.6 into 10 to the power minus 3 meter. So you can eliminate first row and first column. You are left with 3 cross 3 matrix. You are left with 3 cross 3 matrix. This is your second column, third column, fourth column, and second row, third row, and fourth row. Now if you solve these three matrix row equation, you will get the unknown values u2, u3, and u4, and they are coming out to be minus 0.4940 mm, minus 0.3880 mm, minus 0.1940 mm. That means the displacement, direction of displacement which we have chosen, that was the wrong direction. The correct direction will be in the negative x direction. Is it clear? कोई doubt?
No, sir.
Fine. So when you get if you have got the values of U2, U3 and U4, at last we need to find out what? We need to find out element stresses. Element stress already we know that sigma is equal to E into strain displacement matrix into Q or U. Q and U both are same. Either you call it as Q or you call it as U. That is nodal element displacement vector minus alpha delta T. For element number 1, stress present in the element is sigma 1 equal to modulus of elasticity E. And this strain displacement matrix, if you remember, I have told you in previous classes that it is nothing but a 1 cross 2 matrix and is given by minus 1 upon Le and 1 upon Le, where Le is the length of that particular element into. Now, for element number 1, this is my element 1. Element number 1 is comprising of two nodes, node 1 and node 2. So, this nodal displacement vector, this nodal, yes, this nodal displacement vector will be what? It will be nothing but displacement u1 u2 or q1 q2, 2 cross 1 matrix. Q1 Q2 minus alpha is given for first element, delta T is given for first element, Le is length of the first element, which is also we know that is 0.20 mm, 0.20 meter. So if you solve this particular matrix equation, you will get the value of stress present in the first element. Likewise, you can find out the stresses present in the remaining element. If you talk about element number 2, only what will change? This nodal displacement value will change, because I know that for element number 2 is connected between node 2 and node 3. So which displacement value you have to take? You have to take displacement value u2 or q2 and u3 or q3. See, only this thing is changing. Only see Q2, Q3. Le will be same because the second element is again coming out from that bar AB only. Remaining value is same. You can find out the value of sigma 2. Likewise, you can get the value of sigma 3 and sigma 4 for third and fourth element. So in this way, we normally solve the problems related to thermal stress and thermal strain. Any doubt in this problem? Hello? Hello?
No, sir.
Okay. Fine. Then with this, I am ending the today's class over here. We will again meet tomorrow from 3 to 4 p.m. and we will discuss the next sub part of this module. Okay. Thank you. Till then, bye bye.
Thank
So
you, sir.
I will upload
Thank you, sir.
this class lecture by today end. Okay.
Okay, sir.
Okay, sir.
Fine. Okay. Thank you.
Thank you, sir.